computer. Yeah, there we go. All right, you guys. So this assignment, I believe, was a review for you guys from last semester. I think you did implicit differentiation. You weren't differentiating with respect to X. You were differentiating with respect to a variable that was not in the given equation, and that variable is T. The reason I use T is, well, for related rates problems, we're going to be differentiating with respect to T, where T represents time. You need to be using the notation of dy over dt, dx over dt instead of y prime or x prime, because it's really important that you show what you are differentiating with respect to. And what I mean by with respect to is you're coming up with a formula that would allow you to calculate the rate at which y is changing based on how t is changing. So like if t was representing time, it would tell you what's happening to y. How is y changing? Is y increasing or decreasing based on time passing? I gave you guys a worked out example here that I hope was clear and easy to follow along with. But are there any of the questions that we should go through together? And a lot of these had different ways that, like, your steps didn't need to match up with mine exactly, especially the simplifying. But like number 4, you could have used when you were differentiating the left-hand side of the equation. You could have chosen to use either quotient rule or product rule. I rewrote and used product rule because I prefer to use product rule, but you didn't have to do it that way.
I just have a question on number 5. So you multiplied the derivative of dx over dt by 1/2 instead of using the quotient formula, which I thought we were supposed to do there.
Because, oh, okay, so good question. So that sine of y, another way that you could have written the x over 2 is 1/2 times x, right? Like that's the same thing, where 1/2 is just a constant. So you don't need to think about using quotient rule. You could have just thought about differentiating the x with respect to t. You would get, it would be a lot of extra steps using quotient rule, but you should have still gotten the same answer using quotient rule. No, you didn't.
I think something went wrong, but I don't know, yeah.
Should we look at number 5 together? Why don't we just go through number 5 quickly? It's kind of a short problem. Okay, so one thing is, please make sure that you're showing the step where you're stating what you're differentiating with respect to. So we're differentiating with respect to the variable t. And we're trying to find or isolate dy over dt. So you're thinking when you're doing implicit differentiation, you're thinking chain rule, right? Where you're thinking inside function, outside function, right? Chain rule, you differentiate the outside function, you leave the inside alone, and then you multiply by the derivative of the inside. So on the left-hand side of the equation here, sine would be thought of as the outside function, and then y would be thought of as the inside function. Is everyone okay with that? What's the derivative of sine, you guys?
Cosine.
Thank you. So the derivative would be cosine of the outside function. We leave the inside function alone. So still y on the inside. And then we multiply by the derivative of the inside with respect to t. So the derivative of y with respect to t can be written as dy over dt. Just like dy over dx can also be read as the derivative of y with respect to x. It's the formula that tells us how y is changing with respect to how x is changing. So the derivative of y with respect to t is dy over dt. Just unmute yourself, you guys, if you have any questions or something doesn't make sense, and interrupt me. For the right-hand side of the equation, that 1/2 will hang out. And then it's just the derivative of x with respect to t, which is just written as dx over dt. And then our goal is to get dy over dt by itself. So if we divide by cosine of y on each side, I'll do this in 2 steps, but you could do this in 1 step. So you would have 1/2 times dx over dt divided by cosine of y, right? Well, that would end up being just 1/2 cosine of y times dx over dt. Is that okay? Did that help?
Yeah, I think it was just a minor mistake in quotient rule, but yeah, that makes a lot of sense.
Okay. Any other questions, you guys, on this assignment? Okay, well then let's switch over to related rates. So I just wanted to talk to you guys about a couple, I think I put on the agenda. I want you to think about a couple situations. So the first one was filling up your water bottle. So let's say, I think all of you guys probably have some sort of cylindrical water bottle. And if I'm filling up my water bottle at the fridge, right, water's pouring into my, let's say it's an empty water bottle to start. What are some measurable quantities that would be changing as I'm filling up my water bottle? Like, what are some things that would be changing?
Volume.
Volume, the volume of the water that's in the bottle, right? The volume would be increasing or decreasing as I'm filling it?
Increasing.
Increasing. And then if I were to pour water out of the bottle, then the volume would be decreasing. What's something else? What's another quantity that would be changing as time is passing? What's another quantity that might be changing?
Maybe the mass.
Okay.
Like if it gets heavier.
Mm-hmm. Okay. Anything else, you guys? What about, so if my water bottle is empty and I start filling it, the water level would be increasing as time is passing. Now for a cylindrical water bottle, the diameter of the water, like once it fills and covers the bottom, as time is passing, the diameter of the water that's in the bottle would not be changing as time is passing, neither would the radius. If I were filling up a cup, like a Yeti cup, as time is passing, well, this cup does have different diameter or radius for the water that would be inside it as time is passing. So that then it would be changing, but not in my cylindrical cup. So the shape will end up of the container will end up affecting some aspects of what quantities are changing as time is passing. The other example that I have on here is thinking about blowing up a balloon with helium. You can also think about blowing up a balloon just with your mouth, but with helium, that will make the balloon rise. So if we were blowing up a balloon with a helium tank, the volume of the balloon would be increasing, but the volume of helium in the tank would be decreasing, right? Because that helium is being transferred into the balloon. The diameter of the balloon or the radius would be increasing. What else? Are there any other quantities that we could think about would be changing in that situation? The surface area, maybe of the balloon would be increasing. But the idea is that there's those quantities that are changing as time is passing are related to each other. Like you could come up with some sort of relationship between those quantities. You could then also say that there is a relationship between the rates of change of those quantities as time is passing. Like for the water bottle, the rate at which the volume of water is increasing is also related to the rate at which the water level is increasing. So you could say that those rates are related. Anytime we're talking about a rate of change, an instantaneous rate of change, we're talking about a derivative, right? We can use derivatives to calculate instantaneous rate of change, the rate of change at a moment in time. So related rates problems are a type of problem that are an application of derivatives. You guys studied derivatives all last semester. You learned all of the different rules of differentiation or ways to find a derivative. And then use your derivative as a formula for calculating instantaneous rate of change. And you maybe did some examples of that or some problems. So we're going to spend a few days of studying this type of problem because they're interesting. And I think there is, you guys do, some students usually have some anxiety around word problems, but I want you guys to get comfortable with this type of word problem, especially we're going to continue on this semester studying some more applications of derivatives. So to start here, this is just kind of what I've already explained. But for related rates problems, you're basically given a rate or rates, and you're being asked to solve for another rate. So you need to come up with the relationship between the quantities whose rates of change you're concerned with. And then you can derive the relationship between the rates of change by using implicit differentiation. And all of the problems we're going to be looking at are going to be using implicit differentiation where we're differentiating with respect to time. So we're thinking, well, what's happening to this quantity? What's happening to volume as time is passing? What's happening to height as time is passing. So from having the relationship between the quantities, you differentiate, and then that gives you the relationship between the rates of change. And you can solve for whatever unknown rate it is that you're asked to solve for. We're going to look at a pretty simple example and work through that together. And then I'm going to go through the steps that you're going to be following for these problems. Does anyone have any questions or comments before we start looking at this first example? Okay, you guys feel free to interrupt me. Just unmute yourself. Tell me to stop, slow down, ask me a question, whatever you need. So we're looking at the moving particle example. So I want you guys to think about some sort of like a particle, like a dust particle that's floating through space, or let's think about it moving through two-dimensional space, where we can map out its movement in the XY plane. And let's say that this particular dust particle is moving in a pattern that can be mapped out with this equation, x squared minus 4y squared equals to 9. Does anyone know what the graph of this equation looks like? I don't know if you guys have studied conic sections, or if maybe last year you studied conic sections. So this is a hyperbola. Okay, its graph kind of looks like that. So the particle is traveling in this pattern. So when the particle is at the point 5, -2, which is a point on this graph. So at the moment that the particle passes through that position, that point, we're given that its x coordinate is increasing at a rate of 3 units per second. And we want to figure out how fast the y coordinate is changing at that particular moment. So at that instant. I have given you the relationship between x and y, right? I've given you the equation that represents the relationship between the x coordinate and the y coordinate, right? Since the particle, we're thinking of the particle moving around in the xy plane. As it's moving, the values of x are changing as well as the values of y. And they're changing in the same way that x squared minus 4y squared equals to 9, those points are. So for related rates problems, you're given a rate or rates and asked to solve for a rate. The rate that we're given in this problem, I'm going to state. And it's right here. It says the x coordinate is increasing at a rate of 3 units per second. So as time is passing, x is changing at a rate of 3 units per second. And I can write that as dx over dt. And since it says that it's increasing, that means that dx over dt will be equal to positive 3 units per second. If it said decreasing, then I would say that dx over dt was equal to negative 3 units per second. So that's the rate that we're given. And the rate that we're trying to find is how fast the y coordinate is changing. So we're trying to find dy over dt. And you can tell that the slopes of the tangent lines at the points on a hyperbola is going to be changing. So it's not going to be a constant rate. So we want to solve for dy over dt at the moment that the particle is passing through 5, -2. That's describing the moment in time. So we would say we want to find dy over dt when the particle is in the position 5, -2. So I'm going to pause there for a second. Does anyone have any questions up to here? I've currently stated the rate that we have been given, as well as the rate that we're trying to solve for and when. Are you guys okay with the notation that we're using? Okay. So for this problem, I've given you the relationship between the quantities that are changing. I've given you the equation for X and Y. That's not always the case. You'll have an example today where we have to come up with the relationship on our own. But since we're given the equation, we can go ahead and now derive the relationship between the rates, dx over dt and dy over dt. So we're going to differentiate that given equation with respect to t. And I'm going to state that I am differentiating with respect to t, and this is an important step. So then we're differentiating with respect to t, thinking chain rule. When I differentiate the x squared with respect to t, that'll be 2x times dx over dt, because I'm thinking of the square as the outside function and the x is the inside function. So when I differentiate the outside, I bring the 2 down, I subtract 1 from the exponent. I leave the inside alone, which is the x, and then I multiply by the derivative of the inside with respect to t. So the derivative of x with respect to t is written as dx over dt. Then I go to differentiate the next term. That would be minus 8y times dy over dt. And to differentiate the right-hand side of the equation, since it's a constant, that's just going to be 0. Any questions? So we've come up with the relationship between dx over dt and dy over dt. You're trying to solve for dy over dt. So if you wanted to, you could get dy over dt by itself on one side of the equation from here, or what you can do is plug values in that you know, and that's what I'm going to do, because I would prefer to solve for dy over dt with that numbers already plugged in. Like dx over dt is equal to 3, so I'm going to replace the dx over dt with 3. X is 5, so I'll replace x with 5, and y is -2, so I'll replace the y with -2. So plugging those values in, oops. And then solving for dy over dt. So what that would end up being 30 plus 16 times dy over dt. So if I subtract 30 and divide by 16, I'll get dy over dt equals to negative 15/8. And then to figure out what the units would be for the rate, I think, okay, well, what are the units for y? And for y, I think we're just saying units since x was just in units as well, and we're in the xy plane. And then what are the units for time? And time is being measured in seconds. And I know that from looking at the given rate. So it'll be units, dy over dt will be in units per second. And since I ended up with a negative value for dy over dt, that tells me that y is going to be decreasing as time is passing. And when we write our sentence to summarize, because this is a word problem and we want to summarize in a complete sentence, we're not going to write negative 15/8 in that sentence. We're going to interpret the negative. So we can say something like, the y coordinate is decreasing at a rate of 15/8 units per second when the particle is at 5,-2. So we want to make sure we describe the instant that's the rate of change of y.
Can you zoom out a little bit?
I can. So you guys, we're going to be following a similar set of steps for all of these problems, where, well, this one, there wasn't a picture to really draw, but if possible, it's nice to be able to draw a picture, especially if you're visual, very visual, to draw a picture and label the picture with the quantities that are changing. So pick variables that you want to use for the different quantities that are changing. Determine which rate it is that you're given. So state the given and then also the rate that you're solving for. And then you want to come up with the relationship between the quantities that are changing. So like, let's say that let's go back to the water bottle example, right? This is a cylinder. Let's say that I was given the rate at which the height of the water level was changing, and I was being asked to solve for the rate at which the volume was changing. Well, that means that I would need an equation that relates volume and height. Because then when I take the derivative, I want there to be a dv over dt and a dh over dt in that equation. And if I'm not given any other information about other rates, well, that means that I need to have an equation that only has volume and height in it, so that I don't have extra rates in there whenever I'm trying to plug in values, and then I wouldn't have a rate that I know about. We'll have some examples for that'll make a little bit more sense. Not today, but coming in. Once you have the relationship between the quantities that are changing, so once you have your equation, you'll differentiate with respect to t. After you've differentiated with respect to t, where you have the relationship between the rates of change, that's when you'll plug in values that you know. You don't want to plug in values before you take the derivative. The only time you can plug in a value before you take the derivative is if it's for a quantity that's not changing as time is passing. So like in the water bottle example, the diameter or the radius of the water wouldn't be changing as time is passing. That rate of change would be 0. So you could actually plug in that value if you had a formula that required the radius or the diameter. You could plug in that value because it's not changing and then take the derivative. And then after you've plugged in values, you're just solving for the rate that you're being asked to solve for. So we're going to look at the melting snowball problem next. And I've given you the formula for volume of a sphere here. So I've actually given you guys the equation. You don't have to come up with it for this particular example. So a spherical snowball with an outer layer of ice melts so that the volume of the snowball decreases at a rate of 2 cubic centimeters per minute. How fast is the radius changing when the diameter of the snowball is 10 centimeters? And then I've given you the equation for volume of a sphere. So if you think about a snowball melting, the snowball as time is passing is getting smaller and smaller, so it makes sense that the volume would be decreasing. The question is asking for how fast the radius is changing. So as time is passing, we would expect the radius to be increasing or decreasing.
Decreasing.
Decreasing as well, right? So that means that we're expecting the rate that we're being asked to solve for to be negative, since we would expect it to be decreasing. And if we get a positive value, we know that something funky happened. So going through the steps that I have outlined above and that we went through with the previous example, let's go ahead and state our given rate, and we'll also state the rate that we're trying to solve for. So how would I write the rate that we are given here?
dv over dt.
Right, so dv over dt represents the rate at which volume is changing. And what would dv over dt be equal to?
2 centimeters cubed per minute.
Okay, close. Remember, you need to pay attention to the wording here. We're given that the snowball, the volume of the snowball is decreasing.
So negative 2 centimeters cubed per minute.
Yeah, we have to interpret that, the decreasing. So negative 2 cubic centimeters per minute. And that's where it's really important to think about like the actual situation. Because if we had used 2 cubic centimeters per minute, that would have given us a sign error in our final answer where we would have ended up with maybe a positive rate, and that doesn't make sense. Okay, so that's the rate that we're given. We are trying to find, how can we represent the rate that we're trying to find?
dr over dt.
We're trying to find dr over dt, and it gives us that we are trying to find how fast the radius is changing, right? So dr over dt represents the rate of change of the radius when the diameter of the snowball is 10 centimeters. So I can say when, I'll use d to represent diameter, 10 centimeters. However, looking at the formula that we've been given for volume of a sphere, And knowing that we're trying to solve for dr over dt, that tells me that my equation should only have volume and it should only have radius. So v and r should be the only variables in the equation, which is what we have. It's what we're given. That's good. Because when we differentiate, we just want to have a dv over dt and a dr over dt. We don't want a dv over dt because we don't know anything about the rate at which the diameter is changing. But it'll be the same as what the radius is changing. So given that the moment in time that we're solving for dr over dt, the diameter is equal to 10 centimeters, we know that the radius would be half of that. So the radius would be 5 centimeters at that moment in time. So since we're given our equation here that relates volume and the radius, we're going to just be able to differentiate with respect to t. So I have to write that out. I'm going to pull the 4/3 pi out because that's just a constant. And then when I differentiate the left-hand side, well, if I'm differentiating v with respect to t, that's just dv over dt. And then to differentiate the r cubed with respect to t, the cube, the third power is the outside function, r is the inside function. So when I differentiate the outside function, I'll multiply that 4/3 pi by 3, where the 3's would cancel, and we would be left with 4 pi. I subtract 1 from the exponent and leave the inside alone. So that's the r squared. R is the inside function. And then we multiply by the derivative of the inside with respect to t, which will be dr over dt. And then we're ready to plug values in, if everyone's okay with that. So I'm plugging -2 in for dv over dt. I'll plug 5 in for r. And then we'll be able to solve for dr over dt. So that ends up being -2. If you can do the algebra of all this in one step, that's great. If you need to write out the steps, that's fine too. We would be dividing each side by 100 pi. So that would leave us with dr over dt being equal to -1 over 50 pi. And then in thinking about what our units will be for dr over dt, we want to think, well, what units would the radius be measured in? If volume is cubic centimeters, what units would the radius be measured in?
Just
Meters.
centimeters.
Yeah, just centimeters. And then time is being measured in, it looks like, minutes. So centimeters per minute. And we were expecting to get a negative value for dr over dt, right? So that's good. In our sentence, we can summarize, in our sentence that summarizes our answer, we want to interpret that negative. So we'll say something like, the radius is decreasing at a rate of 1 over 50 pi centimeters per minute. If you wanted to figure out the decimal approximation of that, like that's okay too. Maybe round to 3 decimal places. The thousands place. So when the diameter, or you could say when the radius, but I'll put when the diameter of the snowball is 10 centimeters. I'm sorry, you guys, I hate keeping you on Zoom for the whole Zoom period. But I do want to get through one more example with you guys. Any questions about anything up to here? Okay, so the last example that we're going to look at together today is the sliding ladder example. And every calculus textbook has a sliding ladder problem, at least one. It's just one of those common basic related rates problems. So before I even read the problem, think about a ladder leaning against a wall. If you take the bottom of the ladder and you pull it away from the wall, that's going to make the top of the ladder slide down the wall. If you push the ladder in, the bottom of the ladder in towards the wall, that's going to make the top of the ladder slide up the wall. So the distance of the bottom of the ladder to the wall is going to be related to the distance of the top of the ladder to the floor. And their rates of change are also going to be related. So if I label this picture, the ladder that we're dealing with in this particular problem, we're given is 20 feet long. Now, the length of the ladder is not going to change as time is passing. But as time is passing, if we're thinking about pushing the bottom of the ladder in or pulling it out, well, this distance here will be changing, and therefore I could label it with a variable to represent the fact that that distance will vary. I'm going to call that distance X, but it doesn't matter. You can pick a different variable if you would like. And then I'm going to call the distance from the top of the ladder to the ground. I'm going to call that Y. That's where it's important, or it's helpful if you have a picture and you're labeling that picture for me, so I can see how you're interpreting or how you're labeling the different quantities. So for this particular example, a ladder that's 20 feet long leans against a building. If the bottom of the ladder slides away from the building horizontally at a rate of 4 feet per second, how fast is the ladder sliding down the house? I've switched from building to house. Let's call that a building. How fast is the ladder sliding down the building when the top of the ladder is 8 feet from the ground? So based on the picture, the way that I have it labeled, what rate are we given?
.4 feet per second
Yes.
as dx over dt.
Thank you. Yes. So that's dx over dt. We're given the rate at which x is changing. And since the ladder's being pulled, it says sliding away, it would be positive 4 feet per second because x will be increasing as time is passing. If it said that we were pushing the ladder or sliding the bottom of the ladder towards the house where x was decreasing, then we would be using negative 4 feet per second. And we are trying to find how fast the lighter is sliding down the building. So which rate is it that we are solving for?
dy over dt.
Thank you. When the top of the ladder is 8 feet from the ground. So when y is equal to 8 feet. So at that instant, that's the rate that we're solving for. Now for this problem, unlike the other two examples, we're not given an equation. So this is also where sometimes drawing the picture can be really helpful. Because we need to come up with an equation that relates x and y, right? We're given dx over dt. We're trying to solve for dy over dt. So we need an equation that has x and y in it. Looking at this picture, what is a relationship between x and y that we could use?
Well, it's a right triangle, so you can maybe do Pythagorean theorem.
We have a right triangle. You can all see that. And that means we can use the Pythagorean theorem, right? Because x squared plus y squared would be equal to 20 squared. Handy dandy Pythagorean theorem. So in order to derive the relationship between the rates, we're going to differentiate that equation. So we'll differentiate with respect to t, x squared, y squared, and 20 squared is 400. Okay, so then differentiating, that'll be 2x times dx over dt plus 2y times dy over dt equals 0. I've differentiated. I can plug values in. So I'll replace dx over dt with 4. I can replace y with 8. And I'm trying to solve for dy over dt, but I don't have a value for x. Well, since I know that at the moment in time that I'm solving for dy over dt, y would be equal to 8, I can go back to that equation, my Pythagorean theorem equation, and I can solve for what x would be equal to at that moment. So x squared plus, if I plug in the 8 squared equals 400, I would get x squared equals to 336. So x would be equal to the square root of 336, and I only care about the positive value because x represents a length. If you want to, you can leave it as the square root of 336, or you could simplify, that's 4 root 21. And x is being measured in feet. So then we can plug in 4 root 21 for x. Okay, and then solving, that would be 32 root 21 plus 16 times dy over dt equals 0. If I subtract by 32 root 21 on both sides and divide by 16, that'll be dy over dt equals negative 2 root 21. So y would be decreasing, and that makes sense, right? We're in talking about the situation, if we're pulling the bottom of the ladder out, that's going to make the top slide down the wall, which means that the distance between the top of the ladder and the ground is going to be decreasing as time is passing. Y is measured in feet. time is measured in seconds, so feet per second is our unit. And then to summarize, we can say the ladder is sliding down the wall. That's how I'm going to interpret that negative. At a rate of 2√21 feet per second when the top of the ladder is 8 feet from the ground. So like I said, we're going to spend a few days on related rates. I would like you guys to watch the videos for the water tank example as well as the sand pile. Water tank is like a 5-minute video. Sand pile is a little bit longer because there's a couple parts to it. And then attempt those 2 problems from the textbook. I did post, I think most of you guys, you've gone through a semester. I hope you have your textbook, but if it's easier, I did post a PDF of our textbook to our main Schoology page. I'm gonna hang out here. I think what time does this class go until?
It ends at 9:39.
Thank you. So there's 10 more minutes. I'll hang out for those 10 minutes. If anyone wants to talk to me, ask any questions, you can. How do I stop recording? Stop.